Okay, let me give a brief introduction of how does this software work. This software is being designed on LabVIEW platform, which is responsible to heal any permanent unidirectional stuck-at faults occurring in an FPGA device. Let's have a look on the options available here. As I mentioned earlier, that this software communicates with the FPGA device through UART interface. So here we can set the option which COM port it's gonna communicate. It communicates at a baud rate of 38,400 bits per second. Also, these are the fault indication LEDs. Since our demo application consists of two tiles, so these LEDs indicate a permanent fault in any of them. T1 corresponds to tile 1 and T2 corresponds to tile 2. So here are the full bit stream downloading option. Downloads a full bit stream to reconfigure the whole device. The software is designed in such a way that it runs the bitstream downloading commands on a Xilinx command shell at the back end right here from this software, and thus we don't need to run Xilinx impact tool. We have designed it in such a way because whenever an error occurs in FPGA, this software identifies which tile of FPGA is faulty and auto downloads its corresponding partial bit file. The Retrieve Original button retrieves the original functionality of our demo application via downloading a partial bit stream. We need to recover the original functionality first in order to test different erroneous conditions. Here are the error introducing bits. These error introduction bits introduces an error at the runtime on FPGA. Since the differential based partial reconfiguration allows us to change the contents of any specific LUT, so using this technique we generated a partial bit files with LUT contents changed. This is the best way to introduce bit flip errors during runtime. Alright, so temporary error C1 T1 C2 T2 introduces a temporary error in the original functions of cell 1 of tile 1 and cell 2 of tile 2. We will see in the practical demonstration that the actual functionality will keep on going because the spare function immediately takes over the functionality of a faulty original functions. Alright, so permanent error C1 T1 introduces a permanent stuck-at-1 fault in cell 1 of tile 1. During the demonstration, you will realize that first the error introducing bit is downloaded and causes the permanent fault in T1. The fault-tolerant code then sends the frame back to this software and it will identify where the fault actually is. It then immediately downloads the corresponding partial bit stream of tile 1 to reconfigure it. Similarly, permanent error C2 T2 introduces a permanent stuck-at-0 fault in cell 2 of tile 2. And the last option, permanent error T1 T2, both introduces a permanent error in tile 1 and tile 2 at the same time in order to demonstrate the functionality of a permanent error handler. It introduces stuck-at-0 fault in cell 4 of tile 1, stuck-at-1 fault in cell 4 of tile 2, stuck-at-0 fault in cell 3 of tile 2. Here we introduce one error in tile 1 and two errors in tile 2. This demonstration shows you that when the tile is healed, all the errors present in this tile are healed at once, which is the unique feature of our proposed architecture. Also, according to the architecture just described before, tile 1 heals first as it is placed on the left side of a die and then it heals tile 2. Since the recovery process is so fast, so in order to let the viewers observe the process, an optional reconfiguration delay dial is given. It introduces a delay of 0 to 3 seconds in between error introduction and its auto recovery.